lecture, I will state and prove Weisner's theorem, which makes it easier to compute the Mobius function of a poset when we know that it is a lattice. So the theorem is the following. Let L be a finite lattice with a least element 0 hat and greatest element 1 hat. Then for every element A in L that is not equal to 1, that is not equal to 1 hat, we have the Mobius function of L between 0 hat and 1 hat is minus the sum over x in L such that x is not equal to 0 and x meet A is equal to 0 hat of mu of x comma 1 hat. So just to understand what this theorem is saying, let's recall how we compute Mobius functions anyway. So normally we would say that the Mobius function of L is, right, this is from the definition of Mobius function, we would have to sum over all x not equal to 0 mu L x 1 hat. Now this sum could be huge, but by wisely choosing A, we can reduce the extent of this sum. What it's saying is that the contribution of the remaining terms where x wedge x meet A is non-zero will all cancel out. Let me just, before giving you the proof, let me give you an example. Let's revisit pi n again. We had already computed the Mobius function here, but that involved a clever trick. And with clever tricks, you don't really know whether, you know, how they were arrived at and whether you can apply them in a more general situation. So let's do this using Weisner's theorem. And so what we'll do is just take A to be something large in the partial order on set partitions. So what I could do is I could take A to be 1, 2 up to n minus 1 and put n in a different block. So A is not allowed to be 1 hat here, but the next best thing I can do is take something that's covered by 1 hat. And now if you take mu pi n 0 hat 1 hat, well, this is going to be the sum over x not equal to 0 hat x wedge A is equal to 0 hat of mu x 1 hat. So now you ask, what are the set partitions whose meet with 1 to n minus 1 to n is actually equal to the discrete set partition? And so this set partition X must separate 1 from 2, 2 from 3, 3 from 4, and so on. So the first n minus 1 elements of the set 1 to n must be in different blocks. So this is the sum over, so this will be the sum over set partitions of the form. So we'll say I can be allowed to be with n for each I. So I goes from 1 to n minus 1. And then we will take the set partition which has 1, 2, and then I gets blocked with n, and then n. Okay, so there are n minus 1 of these. But if you look at this set partition, so this is still mu pi n, this interval is isomorphic to pi n minus 1. So this is equal to minus 1, I goes from 1 to n minus 1, mu pi n minus 1, 0 hat, 1 hat, because here there are n minus 1 blocks, and we've seen how every interval in the poset of set partitions is isomorphic to a full poset of set partitions. So this turns out to be just minus n minus 1 mu pi n minus 1, 0 hat, 1 hat, and using induction you can easily show that mu pi n of 0 hat, 1 hat is equal to minus 1 raised to the power n minus 1 factorial, starting with the base case where n is equal to 1. Now let's get to the proof of Weisner's theorem. To prove Weisner's theorem, we'll introduce what algebraists may call the basic algebra over basic semi-simple algebra over the complex numbers. So we just define an algebra AL. So L is a lattice here, and let's define AL to be the algebra consisting of all it's as a vector space, it's just a vector space with bases indexed by L. So it's alpha x Ex, where alpha x belongs to C, x summation in L. So it's a vector space with bases Ex, x belongs to L. And multiplication will be absolutely stupid here. Ex multiplied by Ey is going to be Ex if x is equal to y, and 0 otherwise. Okay, so this we can do for any set L. We haven't really used the lattice structure. Now suppose L is a lattice. And let's assume that it has well, we can assume it's a finite lattice, or we can just assume that whatever sums we write, that means for every element x in L, the set x prime belong to L such that x prime less than or equal to x is finite. Okay, I'll introduce now a new basis of this algebra AL, which depends actually on the partial order. So define delta x to be sum over x prime less than or equal to x, Ex prime, for every x in L. So by Mobius inversion, we can recover Ex from delta x's by just using Mobius inversion, mu of x prime x delta x prime. Okay, so let's try to compute the multiplication in this algebra in the delta basis now. So delta x times delta y is equal to summation x prime less than or equal to x, Ex prime, summation y prime less than or equal to y, Ey prime. But the only terms that will survive when we multiply this are the terms where x prime is equal to y prime. So this is the same as sum over t less than or equal to x and less than or equal to y, which means t less than or equal to x meet y, et. But this is the same as delta of x meet y. So the lattice structure on L gets beautifully reflected in this basis. Now, based on this, we will give a proof of Weisner's theorem. So now just fix an element A not equal to 1 in L. So let's assume that L is finite lattice with greatest element 1 hat, least element 0 hat, as in the hypothesis of Weisner's theorem, and an element A that is not equal to 1 hat. Now what we'll do is compute delta A times E1 hat in two ways. First, with respect to the basis by expanding in the E basis, and then by expanding in the delta basis. So what we know is that delta is related to E by just summing over x prime less than or equal to x. So what we get is we get delta A E1 hat is equal to summation x less than or equal to A Ex E1 hat. But that is of course equal to 0 because A is less than 1 hat, strictly less than 1 hat, and x is less than or equal to A. So x can never be equal to 1 hat. Okay, so that was easy. Now let's do the same calculation in the delta basis. And this will involve the Mobius function. So if we do in the delta basis, then what we know is that E1 hat is equal to summation x less than or equal to 1 hat mu of x 1 hat and then we have delta x. So this is just the sum of x less than or equal to 1 hat which is all elements in L, and then we have mu x comma 1 hat and delta x wedge A, x meet A. Now for any y in L, compare the coefficients of delta y in this 0 and in this vector. These are equal, right? So what we get is that in the first expansion the coefficient of delta y is 0, and so what we get is 0 is equal to sum, and here we get x wedge A is equal to y mu of x 1 hat. It's the coefficient of delta y in this expression over here. And now if we take y equals 0, this gives that 0 is equal to x wedge A equals 0 hat mu of x comma 1 hat. And now we take 0 comma 1 hat, take x equals 0 to one side, and so we get mu of 0 hat comma 1 hat is minus x wedge A equal to 0 hat, x not equal to 0 hat because that's the term I took to the other side, mu of x comma 1 hat. And that's the statement of Weisner's theorem.